The real reason candidates fail Google's SRE interview.
Most candidates don't fail because of coding. They fail in the NALS round. It's unstructured, chaotic, and even senior engineers often stumble. In this video, I'll walk you through how to approach it with structure, and how to practice for it properly.
What is NALS?
NALS stands for Non-Abstract Large System Design. It's not about drawing boxes on a whiteboard. It's about being dropped into a messy, large-scale system and reasoning through outages or failures at Google scale.
What interviewers are scoring?
1. Problem framing, how clearly you define the problem. 2. Mitigation first, do you prioritize user impact before diagnosing the root cause? 3. Reliability culture, does your thinking reflect a calm, structured, and prevention-focused mindset?
The Google interviewer's lens.
1. Does the candidate clarify scope before diving into fixes? 2. Do they focus on stabilizing the system first, then diagnosing? 3. Do they tie answers to SLOs, automation, and a reliability-first culture? Weak candidates guess. Strong candidates show structure.
1. The interview question.
Imagine you are in the Google SRE NALS interview. The interviewer leans in and gives you this prompt: you are the on-call SRE for a global photo-sharing platform. Everything looks healthy, but you get an alert: uploads from users in South America are consistently 500 milliseconds slower than in other regions. There are no obvious errors, just this persistent slowness. What do you do?
Why Google asks this?
This is a classic NALS prompt. Google is not testing if you can guess the right answer. They are testing if you have a structured mental model of the internet. They want to see if you can systematically navigate the entire request path, from a user's browser in Brazil all the way to a server in a US data center, and reason about every layer in between without panicking. This question separates true systems engineers from application coders.
What this tests.
1. Layered reasoning. Can you think about the full stack, DNS, CDN, BGP, LBS, app, DB, not just the application? 2. Mitigation first mindset. Do you prioritize restoring the user experience before you find the root cause? 3. Calm under ambiguity. Can you impose structure on a vague problem and communicate your thought process clearly, like a real incident commander?
Common mistakes.
1. They jump to a conclusion: it must be the database, or, it is a bad code deploy, without evidence. 2. They forget the network. They focus only on the application and database layers, completely ignoring the vast network infrastructure in between. 3. They only propose a fix, not a mitigation. They get lost in debugging while forgetting that real users are hurting right now.
Framework to tackle it.
1. Clarify. Ask questions to narrow the scope of the problem. 2. Mitigate. Propose an immediate action to reduce user impact. 3. Diagnose. Walk through the layered diagnostic path, from client to server. 4. Fix. State the likely root cause and the long-term fix. 5. Prevent. Propose automation to prevent this entire class of problems from happening again. A model Google caliber answer.
Step 1. Clarify.
Okay, my first step is to clarify the scope. I would ask, is this affecting all users in South America, or only users on specific ISPs? Is the latency a constant plus 500 milliseconds, or is it spiky? When did this start? Did it correlate with any recent rollouts?
Step 2. Mitigate.
Assuming it is a constant latency affecting multiple ISPs, my immediate priority is mitigation. I would propose temporarily routing a small percentage of South American traffic to the nearest healthy edge, like Miami, to see if that restores performance. This contains the blast radius.
Step 3. Diagnose the layered path.
Now, with mitigation in progress, I will start my layered diagnosis. 1. Client and DNS. Are users resolving to the correct regional CDN edge in Sao Paulo? 2. CDN and network path. my primary hypothesis is a network path problem. A constant 500 milliseconds latency is roughly the round-trip time from South America to North America and back. I suspect a BGP route leak or misconfigured CDN policy. 3. LB, app, and DB. Since app metrics are normal, these are less likely, but I would confirm.
Step 4, the fix.
Let's say traceroute confirms traffic is being misrouted to a US East Coast peer. The root cause is likely a network provider accidentally withdrawing a BGP route advertisement. The fix is to coordinate with our network engineering team to adjust BGP local pref to deprioritize the faulty route.
Step 5, prevention.
For prevention, I would propose adding automated per-region network path latency monitoring. If P99 latency to any edge exceeds 200 milliseconds, it should trigger an automated alert and potentially a geo failover.
Now, it is your turn.
What if the prompt was slightly different? If the latency spike was intermittent and spiky, not constant, how would your diagnostic path change? What hypotheses would you prioritize then? Let me know in the comments below.
2. The interview question.
You are the on-call SRE for a global financial services API. After a scheduled certificate rotation, PagerDuty fires with multiple alerts. 1. P99 TLS handshake latency has spiked from 80 milliseconds to over 2 seconds. 2. SSL handshake failures have increased from 0.1% to 5%. Logs show a mix of certificate expired and unknown authority errors. The service itself is healthy, but clients are intermittently failing to connect. What do you do?
Why Google asks this?
At Google, TLS is not just a security layer, it is a critical component of reliability for both internal, MTLS, and external traffic. A single mismanaged certificate rotation can take down services globally. This question tests your ability to debug a multidimensional failure that crosses cryptography, network infrastructure, deployment automation, and client compatibility. It is a deep probe into your systems-level diagnostic skills.
What this tests.
1. Layered debugging. Can you reason about the entire trust chain, from the client's OS to the load balancer to the certificate authority? 2. Automation mindset. Do you recognize that manual rotation is an anti-pattern and propose systemic, automated solutions? 3. Security versus reliability trade-off. Do you understand the nuances of cipher suites and fallback mechanisms, balancing security posture with availability? 4. Composure under pressure. Can you calmly diagnose a trust is broken scenario without jumping to conclusions?
Common mistakes.
1. Fixating on the leaf cert, only checking the main server certificate and forgetting that a broken or missing intermediate certificate is a more common cause of unknown authority errors. 2. Blaming the client, assuming it is a problem with the user's browser or OS without verifying the server-side configuration first. 3. Assuming atomic propagation, believing that a certificate update is instantly consistent across all global load balancers and CDNs. 4. Proposing manual fixes, suggesting that more careful manual rotation is the solution, instead of proposing a fully automated, verifiable pipeline.
Framework to tackle it.
1. Clarify, is it a latency, slow handshake, or availability, failed handshake, problem? All clients or specific ones? When did it start? 2. Mitigate, immediately roll back to the last known good certificate bundle. 3. Diagnose, use OpenSSL to inspect the presented certificate chain and diagnose the fault, expired, missing intermediate, etc. 4. Fix, rebuild the certificate chain correctly and deploy it via a safe, staged rollout. 5. Prevent, design a fully automated, preemptive, and verifiable certificate rotation system. A model Google Caliber answer.
Step 1. Mitigate first.
My first action is to restore the user-facing trust chain. I will immediately trigger a rollback of the certificate deployment to the last known good version. While the rollback is in progress, I will communicate to the incident channel, investigating TLS handshake failures post-rotation. Rollback initiated to restore service. Root cause analysis to follow. This contains the impact before digging deeper.
Step 2. Diagnose the chain.
With the system stabilizing, I will diagnose the fault. I will use a command like openssls_client, connect api.example.com, for 43 show certs from an external machine. My primary hypotheses are 1. Partial rollout, some load balancers got the new cert, while others still have the old, now expired one. 2. Broken chain, the new certificate was deployed without its required intermediate CA bundle, causing clients that do not have that intermediate cache to fail validation. 3. Cipher suite regression, the new configuration changed the preferred cipher suite, causing slower negotiation fallbacks or failures on older clients.
Step 3. The fix.
Let's assume OpenSSL confirms a missing intermediate certificate. The root cause is a faulty packaging step in our deployment pipeline. The fix is to rebuild the certificate bundle to include the full chain, leave cert plus intermediate certs, and roll this forward as a new, versioned release, starting with a single region to verify correctness.
Step 4. Prevention.
This type of manual error is unacceptable. To prevent this, I would propose a fully automated certificate management pipeline. Key features would include 1. Pre-expiry monitoring, alerting if a cert is within 14 days of expiry, not just when it has expired. 2. Staged rollouts, deploying new certs to a canary environment first. 3. Post-deployment validation, running automated, multi-region synthetic TLS handshake tests that validate the full chain immediately after every rollout. If these tests fail, the pipeline should trigger an automatic rollback.
Now, it is your turn.
How would you design a system to guarantee zero downtime certificate rotation at global scale? What specific architectural pattern would you use to ensure the new certificate is fully propagated and validated everywhere before the old one is decommissioned?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you had one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. salary negotiation, recruiter-proof scripts, and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
3. The interview question.
You are on call for a large microservices platform running on GKE. A new configuration is pushed to one of the key services. Within minutes, PagerDuty fires. 50% of pods in the payments service are in a crash loop backoff state. The deployment is stuck in a rolling update, and P99 latency is rising rapidly as healthy pods are overloaded. What do you do?
Why Google asks this?
At Google, everything runs on a container orchestrator, Borg, which inspired Kubernetes. A failing deployment is the most common type of high-stakes incident. Interviewers need to know that you can safely navigate this environment, distinguishing between an application bug and an orchestration-level problem. This tests your fluency in the language of modern infrastructure.
What this tests?
1. Operational discipline. Do you immediately roll back to stabilize, or do you start debugging a single pod while the fleet burns? 2. Kubernetes fluency. Can you use the right kube control commands to quickly gather evidence from events, logs, and deployment states? 3. Systemic thinking. Do you propose prevention that improves the deployment pipeline, for example, linting, canaries, not just the application code?
Common mistakes.
1. Tunnel vision. Trying to debug one pod, kube control logs, without first checking cluster-level events, kube control get events, that might point to an infrastructure issue. 2. Fighting the scheduler, manually deleting pods, hoping they come back healthy, instead of using the proper rollback command. 3. Ignoring the config, assuming it is a code bug when the prompt explicitly mentions a config push, which is the most likely culprit.
Framework to tackle it.
1. Mitigate first. Immediately contain the blast radius by rolling back the deployment. 2. Gather evidence. Systematically collect data from the Kubernetes control plane, events first, then pod descriptions, then logs. 3. Identify the change, pinpoint the exact line of configuration that caused the failure. 4. Fix safely, correct the configuration and roll it forward as a new, safe release. 5. Prevent recurrence, engineer guardrails into the CI/CD pipeline to prevent this class of failure. A model Google Caliber answer.
Step 1. Mitigate, stop the bleeding.
My absolute first action is to stop the bleeding and restore service. I will immediately run kube control rollout undo deployment or payments. This is the safest and fastest way to revert to the previous, known good replica set. While that's happening, I will post in the incident channel, investigating crash loop storm on payments service. Initiated rollback to contain user impact. Isolating the bad configuration now.
Step 2. Diagnose, gather evidence.
With the system stabilizing, I will investigate. I will not look at logs first. I will start at the cluster level by checking events with kube control get events, sort by equals, last timestamp. This will tell me if it is an infrastructure issue like image pullback off or failed mount. Assuming no infra issues, I will use kube control describe pod on a failed pod to check its termination reason. Finally, I will use kube control logs pod name previous to get the logs from the last crashed container instance, as the current one will be stuck in a restart loop.
Step 3. The fix.
Let's say the logs show the application is failing to connect to a Redis instance, and the pod description shows a new environment variable Redis_host was added. The root cause is likely that the config push contained the wrong host name. The fix is to correct the value in our Git configuration, get it reviewed, and prepare a new, versioned release, for example, v1.2.1.
Step 4. Prevention.
To prevent this from happening again, I would propose 2 changes. First, we need config linting in our CI pipeline to validate that all service hostnames are resolvable before a deployment can even start. Second, this change should have been caught by a canary deployment. We must ensure all config changes are rolled out to a small subset of pods first and automatically rolled back if key SLIs, like the pod startup success rate, degrade.
Now, it is your turn.
How would your diagnostic approach change if the first thing you saw in the cluster events was image pullback off instead of a container crash? What layer of the system would you investigate first, and why?
4. The interview question.
You are the SRE for a globally distributed microservices platform that uses short-lived JWTs for service-to-service authentication. PagerDuty fires with a storm of alerts. Service A cannot authenticate to Service B, Service C reports invalid token from Service A, etc. The failures are happening across multiple services and regions, seemingly at random. The central authentication service that issues the tokens appears healthy. Logs on the failing servers show token validation failed, token used before issued, or token is expired even for brand new tokens. What do you do?
Why Google asks this?
Time is a silent, implicit dependency in virtually all distributed systems, from security tokens, JWT, Kerberos, and TLS certificates to database replication and consensus algorithms, Spanner. A failure in time synchronization is subtle, catastrophic, and bypasses most application-level health checks. This question tests if you can reason from first principles. Can you connect a cascade of seemingly unrelated application errors back to a fundamental infrastructure failure?
What this tests.
1. First principles debugging. Do you jump to blaming the auth service, or do you recognize the symptoms of a clock problem? 2. Distributed systems fluency. Do you understand why synchronized time is critical for security, consistency, and correctness? 3. Infrastructure knowledge. Do you know how to check and diagnose NTP or cronny status on a Linux host? 4. Systemic remediation. Do you propose fixing the fleet-wide time configuration, not just manually fixing one drifted node?
Common mistakes.
1. Chasing ghosts in the app layer, spending the entire time debugging the authentication service, which is a red herring in this scenario. 2. Ignoring the pattern, failing to see that random, widespread authentication failures point to a foundational issue affecting all nodes, not a bug in one service. 3. The manual fix trap, suggesting I will SSH into the box and run NTP date. This is a temporary band-aid, not a systemic fix, and does not address the root cause of why the drift happened. 4. Lack of observability, not knowing what metrics to check. A good SRE should immediately ask, what does our dashboard for NTP offset across the fleet look like?
Framework to tackle it.
1. Hypothesize, observe the widespread, correlated auth failures with invalid timestamp errors. Hypothesize that this is a clock synchronization issue. 2. Diagnose, check infrastructure-level metrics for clock drift. Use chronic tracking or NTP-QP on affected nodes to confirm the offset. 3. Mitigate, force a resync on the affected nodes by restarting the NTP daemon to bring them back into tolerance and stop the immediate failures. 4. Fix, investigate the root cause of the drift. Was there a bad configuration push? Are firewalls blocking UDP port 123? Fix the underlying configuration for the whole fleet. 5. Prevent, implement high-severity, fleet-wide monitoring and alerting for NTP offset to catch drift before it exceeds the tolerance of your authentication system. A model Google Caliber answer.
Step 1. Form a hypothesis.
My first thought is that this is not a bug in any single service. The fact that failures are widespread, intermittent, and all related to authentication points to a cross-cutting concern. The specific log messages, token used before issued and token is expired, are classic symptoms of clock skew between the issuing service and the consuming services. My primary hypothesis is a systemic failure in our NTP synchronization.
Step 2. Diagnose the drift.
I would not start by looking at application code. I would go straight to our infrastructure monitoring dashboards to view max and P99 clock offset across our entire fleet. I would expect to see a cohort of machines drifting significantly. To confirm on a specific failing node, would run chronic tracking or NTP stat. An offset of more than a few hundred milliseconds would confirm the diagnosis. Let's assume I find a whole cluster with an offset of +5 seconds.
Step 3. Mitigate and fix.
The immediate mitigation is to force the drifted nodes to resynchronize. I could trigger a restart of the cronid service across the affected fleet via our automation tools. This should restore service quickly. The real fix, however, is to find the root cause. I would investigate recent changes to our base VM image, network ACLs, or configuration management. Most likely, a firewall change blocked UDP port 123 to our internal NTP servers, or a bad config pushed an invalid NTP server address. The fix would be to revert that change.
Step 4. Prevention.
This outage is an unacceptable failure of basic infrastructure hygiene. To prevent it, I would implement two key things. 1. Blocking clock skew alerts. Any production machine whose clock offset exceeds 500 milliseconds should trigger a high-severity, paging alert. This is our canary. 2. Startup health checks. Our service binaries should perform a clock sync check against a trusted time source on startup. If the offset is too large, the service should fail its health check and refuse to start, preventing it from joining the load balancer rotation and causing problems. Time synchronization must be treated as a critical boot time dependency.
Now, it is your turn.
Imagine your JWTs have a 1-minute validity period, NBF or EXP. What is the maximum tolerable clock skew you would allow across your fleet, and how did you arrive at that number? What are the trade-offs in your decision?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you had one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep. Tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
5. The interview question.
You are the SRE for a critical checkout service. Suddenly, PagerDuty fires, P99 checkout latency, freeze, and transaction error rate greater than 10%. Looking at your dashboards, you see your service's health is fine, but you notice a massive spike in HTTP 429, too many requests errors coming from a third-party fraud detection API that every transaction must pass through. You are burning through your hourly API quota in the first 10 minutes. What do you do?
Why Google asks this?
No service is an island. At Google's scale, systems are deeply interconnected, and failures often cascade from external or internal dependencies. This question evaluates your ability to debug beyond your own service's boundaries. It tests your understanding of defensive system design. How does your service behave when the world around it is failing? It is a probe into your grasp of contracts, SLOs, quotas, partnership with other teams, and architecting for resilience in an ecosystem you do not fully control.
What this tests.
1. Defensive design mindset. Do you think about circuit breakers, graceful degradation, and intelligent retries, or does your service just fail hard? 2. Observability depth. Can your monitoring tools clearly distinguish between an error in your code versus an error from a dependency? Can you tell why the quota was exhausted? 3. Incident command and communication. Do you know how to manage a multi-team, or multi-company, incident? Can you clearly articulate business trade-offs, for example, disable a feature to restore primary function? 4. System architecture. Do you propose long-term fixes like caching, batching, or better quota management to prevent future incidents?
Common mistakes.
1. Aggressive retries. Implementing a simple retry loop for HTTP 429s, which only makes the problem worse, retry storm, and burns the quota even faster. 2. Finger pointing. Declaring it is not our problem, it is the fraud API team's fault. A good SRE owns the end-to-end user experience, regardless of where the fault lies. 3. Lack of a plan B. Having no ability to gracefully degrade the service, for example, bypass the fraud check, leaving the entire checkout flow dead in the water. 4. Slow escalation. Wasting time trying to find a bug in your own code when the dashboards clearly point to a dependency issue, delaying the call to the vendor or partner team for a quota increase.
Framework to tackle it.
1. Mitigate. Immediately reduce the call volume to the dependency. This is likely through graceful degradation, for example, using a feature flag to bypass the check. 2. Communicate. Simultaneously, escalate to the dependency owner or vendor for an emergency quota increase. 3. Diagnose. Investigate why the call volume spiked. Was it a new code release, a bot attack, or an organic traffic surge? 4. Fix. Address the root cause, roll back the bad code, block the attack traffic, or get the quota permanently increased. 5. Prevent. Implement proactive quota monitoring, circuit breakers, and caching to make the system resilient to this failure mode. A model Google Caliber answer.
Step 1. Mitigate first, graceful degradation.
My first priority is to restore the checkout flow. I cannot fix the quota instantly, so I must reduce the calls. I will immediately activate our pre-built, emergency fraud check bypass feature flag. This will allow transactions to proceed without the check, albeit with increased business risk. I will post to the incident channel, checkout service is failing due to third-party fraud API quota exhaustion. Activating emergency bypass to restore transactions. This accepts a temporary increase in fraud risk. Simultaneously contacting vendor for an emergency quota lift.
Step 2. Diagnose the spike.
With the service now stable, I will investigate the cause. My hypotheses are 1. Bad deployment. A recent code change is calling the API inefficiently, for example, in a loop, or without a local cache. 2. Traffic change. A flash sale, marketing campaign, or even a bot attack is driving an unprecedented number of transactions. 3. Quota misconfiguration. The quota was accidentally lowered on the vendor's side. I will check our deployment logs against the timeline of the spike. I will also analyze traffic source logs to look for attack patterns or unexpected surges from legitimate sources.
Step 3, the fix.
Let's assume I find that a new release added a feature that calls the fraud API 3 times per transaction instead of once. This is the root cause. While the emergency bypass is active, I will immediately initiate a rollback of that deployment to the last known good version. Once the rollback is complete and call volume has returned to normal, I can safely disable the emergency bypass. The permanent fix is for the development team to redesign the feature to be more efficient.
Step 4, prevention.
This outage reveals a design weakness. I would propose a multi-layered prevention strategy. 1. Proactive quota monitoring. We must have alerts that fire when we reach 75% of our hourly quota, giving us time to react before an outage. 2. Automated circuit breaker. The manual feature flag should be replaced with an automatic circuit breaker. If the fraud API's error rate exceeds 5% for 1 minute, it should automatically open, bypass the check for a cooldown period, and log the event for risk analysis. 3. Caching layer. For certain idempotent checks, we could implement a short-lived cache, for example, Redis, to avoid redundant API calls for the same user within a session. 4. Capacity planning. Quota requirements for all external dependencies must be a formal part of our capacity planning and pre-launch checklists for any new feature.
Now, it is your turn.
What if the dependency was not a fraud check, but a critical payment authorization gateway that cannot be bypassed? How would your mitigation strategy change if graceful degradation was not an option?
6. The interview question.
You are the SRE for a large-scale photo storage service. An alert fires for P99 image load latency greater than 5 seconds. Users are complaining that older photos are taking a very long time to load or are timing out completely. Your dashboards show that the primary SSD-backed hot storage tier is healthy, with normal latency and I/O. However, metrics for the archival coldline storage tier show its time to first byte has spiked from milliseconds to over 5 seconds. The total number of requests to the cold tier has not changed dramatically from the daily average. What do you do?
Why Google asks this?
At scale, not all data is equal. Tiered storage is a fundamental tool for balancing cost and performance. This question tests whether you understand that a system can be healthy from an availability standpoint but still provide a terrible user experience due to performance degradation. It moves beyond simple up or down monitoring to probe your understanding of data lifecycles, cost optimization trade-offs, and how application behavior can create pathological performance cases on infrastructure that is, technically, working as designed.
What this tests.
1. Understanding of trade-offs. Do you recognize that cold storage is intentionally slow for the first byte and that the application must be designed to accommodate this? 2. Workload analysis. Can you move beyond simple metrics, like request count, and analyze the pattern of access? Are you creating a hotspot on a storage medium designed for infrequent access? 3. Application versus infrastructure. Can you correctly deduce that this is likely an application logic problem causing misuse of the infrastructure, rather than a failure of the infrastructure itself? 4. User-centric mitigation. Do you think about managing the user's experience, for example, with loading indicators, as a valid first step, instead of just trying to fix the back end?
Common mistakes.
1. Blaming the storage, immediately assuming the cloud provider's coldline service is broken, without investigating if the application is misusing it. 2. Treating all latency the same, applying the same debugging steps as you would for a hot storage latency issue, failing to account for the unique properties of archival tiers. 3. Ignoring the access pattern, focusing only on the number of requests, which the prompt says is normal, instead of investigating which specific objects are being requested and why. 4. No mitigation plan, having no way to gracefully handle the slow load time in the user interface, leading to ugly timeouts and a poor user experience.
Framework to tackle it.
1. Mitigate, improve the user experience immediately. Display a "preparing your archived photo" message instead of a generic spinner to manage expectations. 2. Diagnose, analyze storage access logs to identify the access pattern. Is a new feature creating a hot spot by requesting the same few cold objects repeatedly? 3. Correlate, compare the timestamp of the incident start with recent application deployments. The root cause is almost certainly a recent code change. 4. Fix, roll back the offending deployment or use a feature flag to disable the problematic code path. 5. Prevent, implement policies and architecture that account for cold storage latency, such as pre-warming data or adding a caching layer for anticipated cold reads. A model Google Caliber answer.
Step 1. Mitigate the user experience.
My first action is to address the user-facing problem. I cannot make cold storage faster, but I can manage user expectations. I will contact the on-call for the front-end team to enable a feature flag that changes the UI for long-loading images. Instead of a generic timeout, it will show a message like, "Preparing your photo from our archive, this may take a moment." This stops the bleeding from a user trust perspective and buys my team time to diagnose the root cause.
Step 2. Diagnose the access pattern.
My primary hypothesis is that a recent application change is misusing the cold tier. While the total request volume is normal, the pattern of requests is likely pathological. I will query our storage access logs, grouping by object path, to see if a small number of objects are being requested repeatedly. This would create a hot spot and overwhelm the time to first byte capacity of the cold tier for those objects. My goal is to find what is being requested, not just how much.
Step 3. The fix.
Let's assume the log analysis reveals that photos with the prefix /U12345/2015 recap/ are being requested thousands of times per minute. I cross-reference this with our deployment history and see a new Photo Memories feature was enabled an hour ago. The feature is generating a recap video using a user's old photos, causing a burst of reads to cold storage. The immediate fix is to use a central feature flag to disable the Photo Memories module. This will immediately stop the pathological access pattern and allow cold storage performance to return to normal.
Step 4. Prevention.
This was a design failure. To prevent recurrence, I would propose 2 key improvements. 1. Mandatory tier-aware design. Any feature that needs to access archival storage must include a pre-warming or rehydration step in its design. The Memories feature should have a background job that identifies the required photos 24 hours in advance and temporarily promotes them to the hot storage tier before the user ever sees the feature. 2. Smart monitoring. We need to implement an alert on a new metric, cold storage hotspot. This alert would fire if the request rate for any individual object or small group of objects in the cold tier exceeds a low threshold, for example, 1 request per minute, catching this specific anti-pattern before it causes a site-wide incident.
Now, it is your turn.
How would you design a cost-effective system to handle unpredictable viral events, where a very old, cold-stored piece of content suddenly becomes the most requested item in your entire service?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google Caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you had one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
the Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
7. The interview question.
You are the SRE for an asynchronous order processing pipeline. An alert fires, Kafka consumer lag 4 orders, topic 1 million messages. A secondary business level alert follows, P99 order fulfillment time greater than 2 hours. Looking at your dashboards, you see that messages are being produced to the Kafka topic at a normal rate, but the consumer group's lag is growing linearly. The consumer service pods themselves are running and not reporting any crashes. Downstream fulfillment systems are idle, waiting for data. What do you do?
Why Google asks this?
Asynchronous, event-driven architectures are the backbone of massive-scale systems, used for everything from log processing to financial transactions. However, their decoupled nature means failures can be silent and delayed. An issue might not manifest as an immediate 500 error, but as a slowly building backlog that becomes catastrophic hours later. This question tests your ability to debug systems where cause and effect are separated by a queue, probing your understanding of flow control, backpressure, and observability for asynchronous workflows.
What this tests.
1. Asynchronous systems mindset. Can you reason about a system that is available, accepting messages, but not healthy, processing them? 2. Queuing theory and observability. Do you know the critical metrics for a message queue, consumer lag, partition balance, processing rate, and how to interpret them? 3. Root cause analysis. Can you distinguish between a problem in the queue itself, rare, the consumer application, or a dependency downstream of the consumer, common? 4. Data safety. Do you prioritize not losing critical data, like orders, over simply clearing the queue?
Common mistakes.
1. Blaming Kafka, immediately assuming the message broker is the problem. In most managed environments, Kafka is extremely reliable. The issue is almost always in the client application or its dependencies. 2. Scaling blindly, immediately trying to add more consumer pods. If the bottleneck is a slow database downstream, adding more consumers will only increase the load on the database and make the problem worse. 3. Ignoring partitions, only looking at the total topic lag. A single stuck partition, for example, due to a poison pill message, can be hidden in the average, but it is often the root cause. 4. Suggesting data loss, proposing to drop messages or skip offsets to catch up. For a critical topic like orders, this is a non-starter.
Framework to tackle it.
1. Assess impact, confirm the scope. Is processing stopped or just slow? Is data being lost? Communicate the known delay to stakeholders. 2. Diagnose the consumer and its dependencies. The queue is a buffer. The problem is with what reads from it. Check consumer logs for errors. Check consumer metrics for latency to its own dependencies, databases, APIs. 3. Isolate by partition, check per partition consumer lag. Is one partition stuck while others are fine? This points to a poison pill message or a hot shard problem. 4. Mitigate, if a dependency is slow, escalate to that team. If it is a poison pill, move the message to a dead letter queue to unblock the partition. If it is a bad consumer deployment, roll it back. 5. Prevent, implement dead letter queues, comprehensive consumer-side monitoring, processing time per message, and lag-based autoscaling. A model Google Caliber answer.
Step 1. Assess and isolate.
My first priority is to understand the bottleneck. The queue itself is working, as messages are being written. The problem lies with the consumers. I will not scale them up yet, that could be dangerous. Instead, I will look at the logs of the consumer pods. Are they logging errors? Simultaneously, I will check our dashboard for the consumer's dependencies. Specifically, I'm looking at the P99 latency for writes to the order database and calls to the inventory service. My hypothesis is that a downstream dependency is slow, causing our consumers to block.
Step 2. Diagnose the bottleneck.
Let's assume the consumer logs are clean, but our monitoring shows that P99 latency for writes to the main orders database has spiked from 50 milliseconds to 15 seconds. This is our smoking gun. The consumers are healthy, but they spend all their time waiting for a slow database, so they cannot commit their Kafka offsets and process new messages, causing the lag to build. I would immediately escalate to the on-call DBA, sharing my findings that the database is the likely bottleneck for the entire order pipeline.
Step 3. The fix.
While the DBA investigates the database, perhaps to kill a long-running query or failover a bad primary, I can prepare to recover. The good news is that no data is lost, it is just queued. Once the DBA gives the all-clear that the database is healthy again, I will monitor the consumer lag closely. The existing consumers should start processing the backlog at a high rate. If the backlog is very large, I might now decide to temporarily scale up the number of consumer pods to clear it faster, now that I know the downstream bottleneck is resolved.
Step 4. Prevention.
This outage revealed a critical architectural flaw. To prevent it, I would propose several improvements. 1. Dead letter queue, DLQ for any non-transient processing errors, for example, a message with malformed data that causes a DB constraint violation, the consumer must automatically move the message to a DLQ after 2 to 3 retries. This prevents a single poison pill from blocking an entire partition. 2. Consumer-side timeouts. The consumer's database client must have an aggressive timeout, for example, 1 second. If the database is slow, the consumer should fail fast, log the error, and retry the message, rather than sitting idle and holding up the queue. 3. Lag-based alerting and auto-scaling. Our alert fired too late. We need an alert at 10,000 messages of lag, not 1 million. We should also configure a horizontal pod autoscaler to add consumer pods automatically when lag exceeds a certain threshold for more than 5 minutes.
Now, it is your turn.
How would your diagnostic approach change if you found that only one partition out of 64 had a massive and growing lag, while the other 63 were perfectly healthy with zero lag?
8. The interview question.
You are the SRE for a search backend. You push out a new configuration to tune a relevance algorithm. Your deployment tool reports a 100% successful rollout. However, within minutes, you get paged for a 15% increase in no results search queries. The error rate is not consistent, some users are fine, others are not. Looking at the service dashboards, you discover that about a quarter of your fleet is logging invalid algorithm parameter on startup and is stuck in a loop, while the other 75% are healthy and serving traffic with the new config. What do you do?
Why Google asks this?
At Google's scale, atomic updates are a theoretical ideal, not a reality. Failures are partial and inconsistent. This question tests your ability to debug a system in a fractured state. It is not about a simple good versus bad version but about a fleet that is dangerously inconsistent. The interviewer wants to see if you trust your tools blindly, the dashboard said 100%, or if you practice, verify, then trust. It is a deep dive into the reality of managing configuration on thousands of machines that can fail in independent ways.
What this tests.
1. Skepticism and verification. Do you question your tooling and seek ground truth from the systems themselves? 2. Observability for state. Do you understand the importance of an application reporting its own loaded configuration version, rather than relying on the deployment system's view? 3. Distributed state management. Can you reason about how to bring a fleet of hundreds of nodes back to a consistent, known good state safely? 4. Resilience and automation. Do you propose solutions that make the config delivery mechanism itself more robust and self-healing?
Common mistakes.
1. Trusting the dashboard, wasting time looking for a bug in the application logic because the config rollout was successful. 2. Playing whack-a-mole, trying to manually SSH into the bad nodes to fix them one by one, which does not scale and does not fix the root cause of the inconsistent propagation. 3. Assuming a rollback is simple, initiating a rollback command without realizing it might also propagate inconsistently, potentially leaving you with 3 different configurations running in the fleet. 4. Ignoring the why, focusing only on fixing the bad config value, but not investigating why the config was not validated or why the rollout tool gave a false positive.
Framework to tackle it.
1. Halt and contain. Freeze all new deployments to this service to prevent further complicating the state. 2. Verify the true state. Use an out-of-band mechanism, like an ad hoc query tool, to ask every node what config version it is actually running. 3. Force convergence. Use the deployment tool to re-push the last known good configuration to the entire fleet to force all nodes to converge on a single, stable version. 4. Diagnose the failure. Investigate why the initial push failed silently on a subset of nodes and why the tooling reported success. 5. Prevent recurrence. Implement closed-loop verification in the deployment pipeline. A model Google Caliber answer.
Step 1. Halt and establish ground truth.
My first move is to put a deployment freeze on this service. We cannot risk making the state of the fleet even more complex. The deployment tool is clearly not trustworthy, so I need to establish ground truth. I will use our ad hoc fleet query tool to hit a debug endpoint on every server, like /configs, which reports the checksum or version of the configuration file it has loaded in memory. This gives me an accurate, real-time map of which servers are good, bad, or stuck.
Step 2. Force convergence to a known good state.
With a clear map of the inconsistent state, my priority is to make the fleet consistent and healthy again. I will not just roll back, I will explicitly trigger a fresh push of the last known good configuration version to 100% of the fleet. This is a deliberate action to force every single node, regardless of its current state, to re-evaluate its configuration against the central source and converge on the correct, stable version. I will monitor my ground truth query until all nodes report running the correct, known good config.
Step 3. The fix and root cause.
Now that the service is stable, I will investigate the root cause. My hypothesis is twofold. 1. The new config value was syntactically correct but semantically invalid for a subset of our servers, for example, servers with a different CPU architecture or library version. 2. Our deployment tool's success criteria are flawed, it only checks if the file was written to disk, not if the application successfully loaded and validated it. The fix is to correct the bad config value, but more importantly, to fix the deployment process.
Step 4. Prevention, closed-loop verification.
This outage was caused by a dangerously optimistic deployment process. I would propose redesigning it to be a closed-loop system. 1. Application-level validation. The application binary must have a startup flag, validate config only, which can parse a new config and return a success or failure exit code without actually loading it. This must be a step in our CI pipeline. 2. Smarter health checks. After a config is pushed, the health check must not only check if the process is running, but also query a/config's endpoint to ensure the correct version is loaded. 3. Automated rollback. The deployment orchestrator must perform this verification. If a configurable threshold, for example, 5% of the fleet, fails to load the new config and become healthy within a deadline, for example, 2 minutes, the orchestrator must automatically trigger a rollback to the previous version and fail the deployment.
Now, it is your turn.
Imagine your config contains a dynamic value fetched from another service at startup. How could this design lead to a similar, inconsistent fleet problem, and what specific mechanism would you add to prevent it?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you had one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
9. The interview question.
You are the SRE for a large e-commerce product search platform. The business analytics team pages you with an urgent issue: sales for our blue widgets category have dropped to 0 in the last hour. You check your primary SRE dashboard's overall search query latency is low, the service error rate is 0, and CPU or memory on the search fleet are normal. Everything looks perfectly healthy. Yet, when you search for blue widgets yourself, you get no results found, even though you know there are thousands of such products in the catalog. What do you do?
Why Google asks this?
This is a test of your ability to debug silent failures. At Google's scale, systems often do not fail with a loud bang, like a 500 error, but with a silent whimper, by returning incorrect or incomplete data. This scenario probes whether you consider data correctness and integrity to be as important as availability and latency. It separates engineers who just monitor system health from those who monitor for business logic correctness and understand the failure modes of complex, sharded data systems.
What this tests.
1. Correctness as an SLE. Do you instinctively understand that a healthy system returning wrong answers is a P0 incident? 2. Systematic isolation. Can you logically deduce a fault in a single shard of a distributed system without an explicit error message to guide you? 3. Deep system observability. Do you know how to go beyond high-level metrics and use targeted debugging, logging, or internal APIs to diagnose a specific data slice? 4. Data lifecycle management. Do you think about data validation, backfills, and reconciliation as core reliability practices?
Common mistakes.
1. Dismissing the alert, assuming it is a problem with the analytics pipeline because my SRE dashboards are green. 2. Boiling the ocean, restarting the entire search fleet, hoping the problem goes away, which hides the root cause and may not even fix it. 3. Lacking a ground truth, having no way to compare the search index's content against the source of truth database to verify its correctness. 4. Inefficient debugging, searching logs for error, instead of forming a hypothesis about sharding and devising a test to prove it.
Framework to tackle it.
1. Validate and hypothesize, confirm the report. The key hypothesis is that the data for blue widgets lives on a single, corrupted search shard. 2. Isolate the shard, use a debug parameter or internal tool to target the search query to each shard individually until you find the one that returns no results. 3. Mitigate, take the problematic shard, and its replicas, out of serving rotation. This contains the problem. 4. Remediate, trigger a process to rebuild the index for the corrupted shard from the source of truth, the product database. 5. Prevent, implement automated, continuous data reconciliation checks and golden query synthetic tests to detect this class of silent failure automatically in the future. A model Google Caliber answer.
Step 1. Validate and form a hypothesis.
First, I will confirm the report myself by running the query. Since my core SRE metrics are green, this is not a typical outage. The symptoms, a specific category of data disappearing while the rest of the system is fine, strongly suggest a sharding issue. My primary hypothesis is that one of our search index shards, the one responsible for the hash range that includes blue widgets, has become corrupted or is serving a stale, empty index.
Step 2. Isolate the fault domain, the shard.
To prove my hypothesis, I need to query each shard individually. I will use an internal debug feature of our search aggregator, like $debug_shard_override equals 5, to route my blue widgets query directly to shard 0, then shard 1, and so on. I expect that all shards but one will return 0 results, as they do not own the data, and one shard should return thousands of results. In this case, I will find that one shard, let's say shard 13, is also returning 0 results. This confirms that shard 13 is the source of the problem.
Step 3. Mitigate and remediate.
With the faulty shard identified, I will first take all replicas of shard 13 out of the serving rotation. This prevents any queries from hitting the bad data. The immediate impact is that all searches for data on that shard will now fail, but this is a known, contained state. Next, I will trigger our automated shard rebuild process for shard 13. This process will delete the corrupted index files and initiate a new indexing job that reads the correct data from our source of truth product database. Once the rebuild is complete and passes validation, I will add the shard's replicas back into rotation.
Step 4. Prevention.
Detecting this manually is too slow. I would propose 2 systemic improvements. 1. Golden Query Synthetics. We will create a suite of synthetic clients that run golden queries every minute. These queries have known, deterministic results, for example, search for product ID 123456, which we know lives on shard 13. If this query ever fails to return exactly one result, it triggers a PagerDuty alert, immediately pointing to the corrupted shard. 2. Continuous reconciliation. I will build a low-priority background service that continuously samples documents from the source database, calculates a checksum of their data, and compares it to the checksum of the same document in the search index. Any mismatch will create an alert for an SRE to investigate, allowing us to catch corruption before it has a major business impact.
Now, it is your turn.
How would you design the continuous reconciliation system to be efficient and not overwhelm the source of truth database, given a catalog of billions of products?
10. The interview question.
You are the SRE for a social media platform. Every hour, exactly on the hour, PagerDuty fires, P99 API latency, freeze, and database CPU utilization greater than 95%. The alerts resolve themselves after about 5 minutes. During this time, the site is extremely slow. Your application dashboards show a huge spike in cache misses against your Redis cluster, but the cluster itself seems healthy, low CPU and memory usage. The database is getting overwhelmed with identical, expensive select queries. What is happening and what do you do?
Why Google asks this?
Caching is the primary defense for backend systems at scale, but misconfigured caching can create spectacular, self-inflicted failures. This question tests your ability to see the system as a whole. The problem is not the cache, the application, or the database in isolation, it is the interaction between them. The interviewer is looking for your understanding of second-order effects and common caching anti-patterns like thundering herds and fixed-time expirations. It is a classic test of proactive, resilient design versus reactive, simplistic implementation.
What this tests.
1. Pattern recognition. Do you immediately recognize the on-the-hour symptom as a fixed TTL or cron job problem? 2. Caching design patterns. Do you know the standard solutions for a cache stampede, such as adding jitter or using stale while revalidate? 3. Systems thinking. Can you connect the dots from a cache miss, the cause, to a database overload, the symptom? 4. Performance engineering. Do you understand the difference between mitigating the immediate fire and architecting a permanent, resilient solution?
Common mistakes.
1. Focusing on the victim, spending all your time trying to tune the database, which is merely the symptom, not the cause. 2. Scaling the wrong component, suggesting add more database replicas. This will not help if all read queries are hitting the same primary and causing lock contention. 3. A simplistic fix, suggesting just increase the cache TTL. This only delays the inevitable and makes the next stampede even bigger if traffic grows. 4. Ignoring the time correlation, failing to use the exactly on the hour clue, which is the single most important piece of data for diagnosing the problem quickly.
Framework to tackle it.
1. Correlate. Immediately link the hourly alerts to a time-based event. Hypothesize a cache stampede due to a fixed TTL on a popular key. 2. Isolate. Use database monitoring to identify the exact query being spammed. Use application logs or code to find the cache key that generates this query. 3. Mitigate. Manually regenerate the value for the hot cache key and set it in Redis to immediately stop the bleeding. 4. Fix. Deploy a code change that adds jitter, a random value, to the TTL of the expiring cache keys. 5. Prevent. Implement a more robust architectural solution, like a stale while revalidate cache or distributed locking for regeneration. A model Google Caliber answer.
Step 1. Correlate and hypothesize.
The fact that this happens exactly on the hour is the smoking gun. This is not random failure, it is a predictable, scheduled event. My immediate hypothesis is a cache stampede or thundering herd. We likely have one or more very popular cache keys, probably for something like the top 10 posts, that are all set with a fixed 3600 second TTL. When that TTL expires, thousands of application threads simultaneously see a cache miss, and they all hammer the database at once to regenerate the same data.
Step 2. Diagnose the hot key.
To confirm this, I would look at our database query monitoring during an incident. I will find the exact, slow query that's being run thousands of times. Let's say it is select asterisk from posts order by score desk limit 10. I will then grep our application codebase for that query to find the associated caching logic. I will find a line like cache.set, top_posts, result, TTL equals 3600. This confirms the root cause.
Step 3. Mitigate and fix.
The immediate mitigation, while the incident is live, is to manually run the expensive query myself, get the result, and use Redis CLI to set the top_posts key back in the cache. This will instantly stop the stampede. The short-term fix is a one-line code change. I will modify the caching logic to add jitter to the expiration. Instead of TTL equals 3600, it will be TTL equals 3600 plus random.randint, 1, 600. This spreads the expirations over a 10-minute window, preventing them from happening at the same second. I would push this fix for immediate deployment.
Step 4. Prevention, architectural hardening.
Jitter is a good patch, but we can do better. I would propose a project to implement a more robust caching library that supports a stale while revalidate pattern. With this pattern, when a cache key expires, the first request gets the old, stale data back instantly, ensuring a fast user experience, and simultaneously triggers an asynchronous background task to regenerate the fresh value. Subsequent requests get the stale data until the fresh value has been populated. This completely eliminates the regeneration latency spike for users and prevents any stampede on the database. For extremely critical keys, we could also add a distributed lock around the regeneration logic to guarantee that only one process ever attempts to refresh the data at one time.
Now, it is your turn.
What are the potential drawbacks of a stale while revalidate caching strategy, and for what kinds of data, for example, financial transactions, user comments, inventory counts, would this pattern be an unacceptable choice?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle is makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you have one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
11. The interview question.
You are the SRE for a global, multi-region application. The US East region suffers a major network outage. You follow the playbook and trigger a global traffic failover, redirecting all US East traffic to the US West cluster via your GSLB. The traffic shift appears successful, but minutes later, PagerDuty goes critical. The US West cluster's CPU is pegged at 100%, P99 latency is in the tens of seconds, and the error rate is over 50%. The cluster, which was provisioned with 2x the capacity needed to handle the failed overload, is completely overwhelmed and effectively down. What is happening?
Why Google asks this?
Failover is not just flipping a DNS switch. This question brutally tests if you understand the deep, second-order complexities of disaster recovery. At Google, simply having enough servers is never the full story. The interviewer is probing for your knowledge of state, dependencies, and performance characteristics of a cold system suddenly hit with massive load. Can you debug a failure of the recovery process itself, while the primary system is already down? This separates engineers who read disaster recovery plans from those who have lived, and fixed, them.
What this tests.
1. Disaster recovery realism. Do you recognize that failover plans often fail in unexpected ways? 2. Systems thinking. Can you reason about cold starts at a cluster level? For example, cold caches, undersized connection pools, auto-scaling delays. 3. Dependency mapping. Do you instinctively look for hidden, cross-region dependencies that did not fail over correctly? 4. Graceful overload management. When the backup plan fails, do you have a backup for the backup? Do you know how to shed load to save the system?
Common mistakes.
1. Assuming capacity is the problem, the prompt explicitly states capacity is sufficient. Saying, add more servers misses the entire point of the question, which is about performance and efficiency, not raw numbers. 2. Tunnel vision on traffic routing, focusing on DNS or the GSLB. The traffic got there, the problem is what happened next. 3. Forgetting state, overlooking the massive performance impact of empty caches, which turns cheap lookups into expensive database queries and causes a cascading overload. 4. Letting it burn, not having an immediate plan to shed load, allowing the failover region to completely collapse into a global outage.
Framework to tackle it.
1. Mitigate, shed load. The US West cluster is dying. Immediately shed load via rate limiting or serving degraded content to prevent a total global outage. 2. Hypothesize the inefficiency. Why is the provisioned capacity not performing? Primary hypotheses are cold caches or a hidden cross-region dependency. 3. Diagnose, check cache hit rate metrics for US West, expect near zero. Check latency or error dashboards for all outbound calls from US West to see if they are timing out trying to reach the dead US East region. 4. Remediate, if it is a dependency, fail it over. If it is a cold cache, you must weather the storm and wait for it to warm up while shedding load. 5. Prevent, the failover plan is flawed. It must be updated to include cache warming strategies, dependency failover drills, and active-active designs. A model Google Caliber answer.
Step 1. Mitigate first, save the remaining region.
My primary system is down, and my backup is on fire. This is now a global outage. My absolute first priority is to save the US West cluster from collapse. I will immediately engage our global load shedding capabilities to drop 50% of incoming traffic, serving a static error page. This is a critical business decision to ensure at least some users can be served. I will announce in the incident channel, failover to US West is causing overload. Shedding 50% of traffic globally to stabilize the serving region. Investigating the source of the inefficiency now.
Step 2. Diagnose the inefficiency.
The cluster has enough provisioned CPU, but its effective capacity is a fraction of what it should be. This is not a numbers problem, it is a performance problem. My top 2 hypotheses are 1. Cascading cold cache failure, the US West caches are empty. Every request is a cache miss, hammering our back-end databases. I will check the cache hit ratio metric for US West. I expect it to be less than 5%, when it should be over 95%. 2. Stranded regional dependency. The service in US West has a hard-coded configuration or service discovery flaw and is still trying to reach a downstream service, for example, a user profile API, back in the dead US East region. I will check the dashboard for outbound RPC latency from US West. I expect to see thousands of connections timing out.
Step 3. The fix.
Let's assume the diagnostics confirm the stranded dependency. I see RPCs to profile service.useast.prod are all timing out. The failover playbook for our service did not include failing over this dependency. The fix is to immediately push a configuration change to the US West cluster, forcing it to use the profile service.uswest.prod endpoint. Once the change propagates, timeouts will stop, requests will be processed efficiently, and the CPU load will plummet. I can then slowly dial back the load shedding to 0.
Step 4. Prevention.
Our disaster recovery plan was a disaster. The post-mortem must be brutally honest. To prevent this, I would lead the effort to implement one. Dependency-aware automation. The failover script must be aware of all downstream dependencies. It should automatically check and remap their endpoints as part of the failover process. This cannot be a manual checklist item. 2. Regular, automated drills. We must conduct full-scale failover drills in a production environment on a quarterly basis. These drills, which can be done by shifting a small percentage of traffic, will exercise the entire dependency chain and catch these configuration drifts before a real emergency. 3. Active-active architecture. For our most critical services, we should push to move from a passive failover model to an active-active one. This is more expensive but eliminates the entire class of cold start and dependency misconfiguration problems, as both regions are always serving live traffic.
Now, it is your turn.
If the cause had been the cold cache problem instead of the dependency issue, how would your mitigation and long-term prevention strategies change? You cannot instantly warm a cache with terabytes of data, so what would you do?
12. The interview question.
You are the SRE for a high-traffic e-commerce storefront. A new feature is launched that adds a user's recent browsing history to the homepage. This data comes from a real-time analytics service. 2 hours after launch, the analytics service suffers a major slowdown. Suddenly, PagerDuty fires, P99 homepage load latency greater than 10 seconds. Your service's CPU and memory are fine, but all of your web server threads are stuck, waiting for a response from the analytics service. The homepage, your most critical page, is effectively down because of a non-critical personalization feature. What do you do?
Why Google asks this?
This is a quintessential test of defensive system design. At scale, any dependency will eventually fail. A senior engineer is expected to anticipate this and build systems that are resilient, not just reliable. This scenario probes your understanding of fault isolation and graceful degradation. Can you architect a system where the failure of a nice-to-have feature does not cause a catastrophic failure of the core product? It is a direct question about your philosophy on building robust, loosely coupled microservices.
What this tests.
1. Defensive programming mindset. Do you instinctively see a synchronous network call to a non-critical service as a major architectural flaw? 2. Understanding of timeouts. Do you know that the absence of a timeout is often more dangerous than an error? Can you explain why? 3. Fault isolation. Do you propose solutions like circuit breakers or asynchronous loading that contain the blast radius of a failing dependency? 4. Operational maturity. Do you have a mechanism, like a feature flag, to immediately disable a problematic feature without needing a full code deploy or rollback?
Common mistakes.
1. Debugging the wrong service, spending all your time trying to fix the analytics service. While it is broken, the real problem is that your critical service is not resilient to its failure. 2. A slow fix, suggesting a code change to add a timeout and then waiting for a full deployment cycle. This could take 30 minutes, while the site is burning. 3. Ignoring the synchronous call, not identifying the synchronous network call on the critical path as the fundamental design flaw. 4. Restarting servers, simply restarting your web servers. This will provide a few seconds of relief before all the new threads get stuck again on the same slow call.
Framework to tackle it.
1. Mitigate. Use a dynamic feature flag to immediately disable the new browsing history feature. This will stop the calls to the slow service and instantly restore homepage performance. 2. Diagnose. Confirm with logs and distributed tracing that all request threads are stuck waiting on the analytics service RPC. 3. Communicate. Inform stakeholders that the new feature has been temporarily disabled to resolve a site-wide outage. 4. Fix. The short-term fix is to add aggressive timeouts. The long-term, correct fix is to re-architect the feature to be asynchronous. 5. Prevent. Mandate timeouts, retries, and circuit breakers for all network calls as a standard library, and require design review for any new dependency added to a critical service. A model Google Caliber answer.
Step 1. Mitigate immediately, feature flag.
My first action is to restore the homepage. The fastest and safest way to do this is to use our feature flag system to turn off the browsing history feature. This will immediately stop the blocking calls to the failing analytics service, freeing up the web server threads and restoring the core homepage functionality. I will post in the incident channel, homepage is down due to a slow analytics dependency. Disabling the new browsing history feature via feature flag to mitigate immediately. Root cause is a missing timeout.
Step 2. Confirm the root cause.
With the site stable, I will confirm the diagnosis. A thread dump of one of the web servers would show every single request thread stuck in the network stack, waiting on a socket read from the analytics service. Our distributed tracing system would paint an even clearer picture. A trace for a homepage load would show 99% of the time spent in a single RPC span to the analytics service, with no timeout configured. This is a critical design flaw.
Step 3. The fix, short and long term.
The immediate code fix, which we would deploy before re-enabling the feature, is to wrap the RPC in an aggressive timeout, for example, 100 milliseconds, and a try or catch block. If the call fails or times out, we will log the error but render the rest of the homepage. However, the correct long-term architectural fix is to make this call asynchronous. The homepage should render the critical content first, and the browsing history module should be loaded via a separate, non-blocking AJAX call from the user's browser after the main page is already interactive. This decouples the availability of the two services completely.
Step 4. Prevention.
This outage was caused by a policy and design failure. To prevent this entire class of problem, I would champion 3 initiatives. 1. A resilience library mandate. All RPC clients used at our company must have timeouts, retries, and circuit breakers enabled by default. It should require explicit effort to make an unsafe, non-timeout protected network call. 2. Strict critical path reviews. Any proposed code change that adds a new synchronous dependency to the critical path of a Tier 1 service, like the homepage, must undergo a specific, rigorous design review by senior SREs. 3. Chaos engineering. We will add a test to our game day exercises that uses a service mesh to inject high latency into non-critical dependencies. This will proactively prove that our critical services can withstand these failures, rather than waiting for a real outage to discover them.
Now, it is your turn.
Describe the core logic of a circuit breaker. What 3 states does it have, and how does it transition between them? Why is it superior to a simple timeout and retry mechanism?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google Caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle is makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you have one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
13. The interview question.
You are the on-call SRE for a major global service. PagerDuty explodes with alerts, traffic from EMEA region has dropped by 90%, APAC latency is infinite. Your dashboards for all your compute, storage, and load balancing systems in the EU and APAC regions show they are perfectly healthy, with near zero CPU utilization. Probes from North America confirm the service is up and fast. However, third-party monitoring confirms that all connectivity attempts from Europe and Asia are timing out. Your cloud provider is reporting no issues. You are effectively invisible to a third of the planet. What do you do?
Why Google asks this?
This question is designed to see if you are truly a systems engineer or just an application engineer. The system, in this case, is the global internet. It is the ultimate "it is not my server, but it is my problem" scenario. It tests your ability to diagnose failures in a complex, decentralized system where you have no direct control. The interviewer wants to know if you can reason from first principles about how packets get from a user to your service, and if you know how to use tooling and communication to influence a solution outside your own walls.
What this tests.
1. Networking fundamentals. Do you know what BGP, ASNs, IP prefixes, and route leaks are? Do you understand that the internet is a trust-based system that can be broken? 2. External observability. Do you immediately reach for tools beyond your own monitoring stack, like public-looking glasses, RIPE Atlas, and BGP monitoring services? 3. Incident command at scale. Can you calmly gather evidence of an external fault and communicate it effectively to parties you have no authority over, for example, other ISPs? 4. Efficient triage. How quickly do you eliminate your own systems as the cause and pivot to investigating the external network path?
Common mistakes.
1. Internal tunnel vision, wasting critical time restarting healthy servers, failing over healthy load balancers, or digging through application logs when all internal signals are green. 2. Blaming the cloud provider, declaring, "It is a cloud outage," without providing any specific evidence of a network path failure. This is unhelpful and slows down the resolution. 3. Using the wrong tools, trying to debug by running ping from your own laptop, which is likely in a working region, and concluding the problem does not exist. 4. Helplessness, throwing up your hands and saying, "It is an internet problem, nothing we can do." A great SRE takes ownership of the problem until it is resolved, even if they cannot fix it directly.
Framework to tackle it.
1. Confirm and scope, verify that internal systems are healthy and that the failure is correlated with specific geographic regions. 2. Hypothesize external fault, based on the symptoms, form the primary hypothesis of a BGP route leak or prefix hijack. 3. Gather external evidence, use geographically distributed probes, for example, Thousand Eyes, RIPE Atlas, to run traceroute and MTR to identify the point of failure. Use public BGP monitors, for example, BGP Stream, Kentic, to check for anomalous advertisements for your service's IP prefixes. 4. Escalate with data, open AP1/Severity1 ticket with your cloud provider's network team and your own internal network engineers. Provide the traceroutes and BGP data as concrete evidence. 5. Communicate externally. Update the public status page to inform users that you are investigating a widespread internet routing issue affecting certain regions. A model Google Caliber answer.
Step 1. Eliminate internal systems.
My first observation is that all my internal systems are green. This is a strong signal that the problem is not with my application, my cluster, or my direct infrastructure. The clear geographical boundary of the failure, affecting entire continents while leaving others untouched, is a classic symptom of a wide area network or routing failure. I will declare this as the primary hypothesis within 60 seconds and direct all efforts away from debugging our internal services.
Step 2. Gather public evidence.
I need to prove where the internet is broken. I will immediately use our external observability platform to launch traceroute commands from probes in London, Frankfurt, and Singapore towards our service's public IP. I expect these traces will not reach our network edge and will instead die or loop within the network of a specific transit provider. Simultaneously, I will use a tool like BGP Stream to look up our IP address prefix. I am looking for a suspicious recent event, specifically a new, unauthorized autonomous system, AS, starting to announce our prefix.
Step 3. Escalate with precision.
Let's say the traceroutes die at ISP X and BGP Stream shows that AS12345, belonging to ISP X, started erroneously announcing our prefix 15 minutes ago. This is the smoking gun. I will immediately open a Severity1 ticket with our cloud provider's Network Operations Center, NOC. The ticket summary will be, suspected BGP route leak from AS12345 blackholing traffic to our prefix. Attaching traceroutes and BGP data. Urgent engagement with their NOC is required. I will also page my own network engineering team to engage in peering discussions.
Step 4. Prevention and postmortem.
While we are dependent on the faulty ISP to fix their mistake, we are not helpless in the future. The postmortem will focus on two things. 1. Detection. We need to have automated BGP monitoring in place. An alert should have fired the moment a suspicious new AS path for our prefix was detected, telling us the who and what before the user impact alerts even began. 2. Prevention. We need to work with our network team to implement Resource Public Key Infrastructure, RPKI. RPKI allows us to cryptographically sign our route announcements, creating a Route Origin Authorization, ROA, that tells the world only our ASN is legitimate to originate this prefix. This allows other major networks to automatically reject the fraudulent announcements from the misconfigured ISP, significantly reducing our vulnerability to this kind of incident.
Now, it is your turn.
Imagine your cloud provider offers a bring your own IP, BYOIP, service. How could using your own IP space, rather than the cloud providers, give you more options to mitigate an incident like this?
14. The interview question.
You are the SRE for a user profile service with a primary replica database setup. An alert fires, P1, DB replication lag greater than 30 minutes. Soon after, customer support reports an influx of tickets. Users are updating their profiles, receiving a success message, but when they reload the page, the changes are gone. Your service availability is 100% and the error rate is 0%, yet the service is fundamentally broken from a user's perspective. What do you do?
Why Google asks this?
This question pierces the veil of simple availability metrics, the 5 nines, to test your understanding of a much more subtle and critical concept: data correctness. At Google, for many systems, returning stale or incorrect data is considered a more severe outage than returning an error. This scenario probes your deep understanding of stateful systems, consistency models, eventual versus strong, and the difficult, real-time trade-offs an SRE must make between consistency, availability, and performance.
What this tests.
1. Correctness over availability. Do you immediately recognize that this silent failure is a critical, user-impacting outage? 2. Stateful system architecture. Can you mentally model the read or write paths in a primary replica setup and pinpoint where the inconsistency is occurring? 3. Database internals. Do you know the common causes of replication lag, long-running queries, network saturation, under-provisioned replicas, and how to diagnose them? 4. Calculated mitigation. Do you understand the performance cost of forcing consistency, for example, reading from the primary, and can you articulate that trade-off clearly?
Common mistakes.
1. Dismissing the problem, saying availability is 100%, so this is not a major incident, which shows a dangerous lack of user empathy. 2. Focusing on the application, trying to find a bug in the application code that returns a false success message. The app is working fine, the data layer is the problem. 3. Rebooting the replica, a knee-jerk reaction that might temporarily help but does not identify the root cause, and the lag will likely return. 4. Premature failover, triggering a primary database failover. This is an extremely high-risk action that can cause data loss if not managed perfectly and is rarely the correct first step for a lag issue.
Framework to tackle it.
1. Acknowledge and mitigate. Immediately treat data inconsistency as a P0/SEV1 incident. Mitigate by forcing reads to be consistent, accepting the performance penalty. 2. Diagnose the lag. Investigate the database layer to find the root cause of the replication delay. 3. Remediate the cause, fix the underlying issue, for example, kill a bad query, scale up the replica. 4. Restore normal operation. Once lag is resolved, revert the mitigation to return to a normal, high-performance state. 5. Prevent. Implement architectural and operational safeguards to prevent this from happening again. A model Google Caliber answer.
Step 1. Mitigate first, restore data consistency.
This is a critical data correctness outage. My first priority is to stop lying to users. I will immediately use a dynamic configuration flag in our service to switch all read traffic from the replicas to the primary database. I will announce this in the incident channel, activating read from primary mode to resolve user data inconsistency. Be aware, this will increase primary DB load by 300% and significantly increase read latency, but it is necessary to restore correctness. Now investigating the source of the replication lag.
Step 2. Diagnose the replication lag.
With users now seeing consistent data, albeit slower, I will dive into the database. My primary hypotheses for the lag are 1. A long-running write on the primary, a single, massive update or a thoughtless alter table could be blocking replication. 2. An under-provisioned replica. The replica might be I or O or CPU bound and unable to keep up with the write volume. 3. A poison pill write, a specific, very large write, for example, a user uploading a multi-megabyte value into a single row, is choking the replication stream. I will use show replica status to check for errors and then show process list on both the primary and replica to find blocking or long-running queries.
Step 3, remediate and recover.
Let's assume I find a developer was running a large, manual update statement on the primary that has been running for an hour. This is the root cause. I will work with the on-call DBA to safely terminate this query. Once the query is killed, the replication stream will be unblocked, and the replica should quickly catch up. I will monitor the replication lag metric. As soon as it drops below a few seconds, I will toggle the configuration flag back to allow reads from the replicas, restoring normal performance. I will then verify with customer support that the user reports have stopped.
Step 4, prevention.
This incident revealed a design flaw and an operational weakness. I would propose 2 key follow-ups. 1. Architectural fix. Read your writes. We should implement a read your writes consistency model. For a brief window, for example, 60 seconds, after a user performs a write, any reads from that same user are intelligently routed to the primary. This provides the consistency users expect without sacrificing the scalability of reading from replicas for all other traffic. 2. Operational fix. Better guardrails. We need stricter controls on manual database access. Any long-running or large-scale data modifications must be executed via an automated, peer-reviewed process that uses safe tools, like point online schema change, to avoid locking the primary.
Now, it is your turn.
How would you implement a read your writes consistency model for a stateless web application fleet at scale? What are the technical challenges you might face with load balancers and connection pooling?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you had one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
15. The interview question.
A month-long data migration to a new user profile schema completed last week, and the old system was decommissioned. Today, a user in France reports their name, which contains an accent, François, is showing as Franois. Soon after, a report from Japan shows a similar issue. You discover the migration script had a subtle character encoding bug. It has been a week, so users have been making new, valid updates to their profiles. You now have a mix of correct data, newly updated data, and silently corrupted data across millions of rows. What do you do?
Why Google asks this?
This is one of the most difficult situations an SRE can face because the damage is already done, hidden, and widespread. There is no rollback button. This question tests your ability to think like a data surgeon. Can you carefully diagnose the scope of the corruption, devise a precise remediation plan, and execute it without making the problem worse? It separates engineers who think in terms of servers from those who think in terms of data integrity, which is a critical distinction for any service that stores user data.
What this tests.
1. Data integrity as priority 1. Do you immediately recognize the severity and treat silent data corruption as a 5-alarm fire? 2. Forensic analysis. Can you devise a non-destructive method to find every single corrupted row in a massive dataset? 3. Safe data manipulation. Can you design a repair script that is idempotent, rate-limited, auditable, and preserves newer, valid user updates? 4. Risk management. Can you articulate the risks of a live data repair operation and explain the safeguards you would put in place, backups, DRY runs, canaries?
Common mistakes.
1. The Big Bang restore, suggesting a full database restore from a week-old backup. This would cause a week's worth of catastrophic data loss for all valid user updates and is a non-starter. 2. A careless update query, writing a simple update, where query to fix the data. This is extremely dangerous. What if the logic is wrong? How do you test it? How do you roll it back? 3. Ignoring new data, designing a fix that overwrites recently updated, valid data with the old, repaired data, thus causing a secondary data loss incident. 4. Failing to validate, not having a plan to verify that the fix was 100% successful and that no new corruption was introduced.
Framework to tackle it.
1. Contain and analyze, halt any further data migrations. Write a non-destructive, read-only script to identify the exact scope of the corruption and generate a list of affected primary keys. 2. Backup and plan, take a fresh, complete backup of the database before attempting any repairs. Write a detailed remediation plan and have it peer-reviewed. 3. Develop a surgical tool, write a repair script that operates on one user at a time, is idempotent, and checks the last _updated timestamp to avoid overwriting newer data. 4. Execute safely, run the script in DRY run mode first. Then, execute it against a small canary set of users. Finally, run it as a rate-limited background job against the full set of corrupted records. 5. Validate and communicate, run the analysis script again to confirm 0 corrupted records remain. Communicate the resolution to stakeholders. A model Google Caliber answer.
Step 1. Halt, analyze, and scope, the do no harm phase.
My absolute first priority is to do no more harm and to understand the exact blast radius. I will immediately ensure any related migration or backfill jobs are disabled. Then, I will write a read-only analysis script. This script will scan every user row, attempt to decode the name field with the incorrect encoding and then re-encode it, and check if it matches the original. This will non-destructively identify potentially corrupted rows. The output will be a definitive list of user IDs that need repair. This gives me my scope.
Step 2. Backup, plan, and tool.
Before I write a single line of modification code, I will ensure a full, consistent snapshot of the production database is taken and secured. This is my undo button. Next, I will author a detailed remediation plan, outlining the logic of the repair script, the safety mechanisms, and the execution strategy. This plan must be peer-reviewed. The script itself will be designed for safety. It will take a user ID as input, fetch the old or corrupted data and the original source of truth data, and critically, check if the last _updated timestamp in the production table is newer than the migration completion time. If it is, it will flag this user for manual review, preserving the new user data. Otherwise, it will perform the repair.
Step 3. Execute with extreme caution.
I will never run this script directly against production in one go. The execution will have 4 phases. 1. DRY run the script against the full list of affected user IDs in a log-only mode, printing exactly what changes it would make. 2. Staging execution, run the script in write mode against a restored backup on a staging server to ensure it works correctly. 3. Canary release, manually run the script for a handful of affected users, perhaps the ones who reported the issue, and verify the fix with them. 4. Rate-limited batch job, execute the script as a background job that iterates through the list of affected IDs at a controlled, throttled pace, with constant monitoring of database load and error rates.
Step 4. Validate and prevent.
After the batch job completes, I will rerun the read-only analysis script from step 1. The expected output is 0 corrupted rows. The post-mortem for this will be severe. The key preventative measure is to change how we do migrations. Future data migrations must include a verification step. The migration tool must, as part of its process, read the data back from the new system, transform it back to the old format, and verify that it matches the original source of truth bit for bit. This closed-loop validation would have caught the encoding bug on the very first record and prevented this entire incident.
Now, it is your turn.
How would your repair strategy change if you discovered you did not have access to the original, uncorrupted, source of truth data anymore because the old system was physically decommissioned?
16. The interview question.
You are on call when PagerDuty fires with a catastrophic alert, critical asset bucket is empty. Simultaneously, hundreds of other alerts fire for missing images, CSS, and JavaScript files. You see in the audit logs that your automated storage janitor service account is executing thousands of delete operations per second against your primary production storage buckets. The script, which is supposed to clean up old, temporary files, is deleting everything. What do you do, in what order, in the first 60 seconds?
Why Google asks this?
Automation is the SRE's greatest tool and greatest liability. This question is a direct and brutal test of your operational discipline in a "the call is coming from inside the house" emergency. The interviewer is not just looking for the right answer, they are looking for the right order of operations. Can you stop the bleeding before you diagnose the wound? It probes your deep understanding of designing safe, reliable automation and your ability to react under the most extreme pressure when that safety fails.
What this tests.
1. Emergency reflexes. Do you have an instinctive, muscle memory response to a destructive action in progress? Do you know how to hit the big red button? 2. Defense in depth. Do you talk about multiple layers of safety, IAM permissions, rate limits, sanity checks, or just one? 3. Risk management. Can you articulate why a seemingly simple script that performs deletions is one of the most dangerous pieces of code in your entire infrastructure? 4. Proactive versus reactive safety. Do you propose solutions that would have prevented the disaster, not just tools for cleaning it up afterward?
Common mistakes.
1. Diagnosing first, trying to blame the script or read its code while production is actively being deleted. This is a catastrophic failure of prioritization. 2. A slow response, suggesting a graceful stop or a rollback of the script's code. These actions are too slow. The only acceptable first move is an immediate, hard stop. 3. Lack of an emergency brake, not having a clear, predefined way to instantly disable a service account or revoke its permissions. 4. Blaming the developer, focusing on the developer who made the change instead of the systemic lack of guardrails that allowed a single change to cause this much damage.
Framework to tackle it.
1. Stop the bleeding. immediately and unconditionally revoke all write or delete permissions for the service account running the script. This is the first and only priority. 2. Assess the damage. Once the deletions have stopped, use logs and storage metrics to determine the exact scope of data loss. 3. Begin recovery. Initiate the documented disaster recovery plan for restoring the storage buckets from the most recent backup. 4. Diagnose the root cause. Now, and only now, investigate the code change that caused the faulty logic. 5. Build guardrails. Implement multiple, robust safety mechanisms to make this class of failure impossible in the future. A model Google Caliber answer.
Step 1. The first 60 seconds stop the bleeding.
My actions in the first minute are critical and executed in a specific order. I will not look at code. I will not look for the commit. I will do one thing. I will go into our Cloud IAM console, find the service account role used by the janitor script, and I will immediately detach the storage.objects.delete permission policy. This is the big red button. It will cause the script to start throwing access denied errors, but it instantly stops the data loss. Only after I have confirmed in the audit logs that the delete calls have stopped will I even begin to think about anything else.
Step 2. Assess and recover.
With the immediate threat neutralized, I will assess the blast radius. I will need to determine which buckets were affected and to what extent. I will then declare a CV1 incident and trigger our formal disaster recovery plan for object storage. This involves using our backup and versioning systems, like object versioning in GCS or S3, to begin restoring the deleted files. I will communicate to stakeholders that we are in recovery mode and provide an ETA once the scope is clear.
Step 3. Root cause analysis.
Now that the fire is out and recovery is underway, I can safely investigate the root cause. I will look at the recent commits to the janitor script. I expect to find a change where a regular expression or a filter condition was broadened incorrectly, causing it to match production assets. The why is not just a developer made a mistake, but why did our system allow a single, unreviewed, or poorly tested change to a non-critical script to destroy production.
Step 4. Prevention. Never again.
This incident was a catastrophic failure of our safety engineering. To ensure this never happens again, I would mandate a multi-layered defense. 1. Logical sanity checks. The script must, before performing any deletions, check the number of objects it is about to delete. If that number is ever more than 1% of the total objects in the bucket or exceeds a static threshold, for example, 1,000 objects, the script must immediately abort and page an SRE. This is a critical circuit breaker. 2. DRY run by default. All executions of this script must run in a DRY run mode first, which logs the full list of objects it would have deleted. This list must be written to a log, and a human or a separate, trusted verification system must approve it before the script can be rerun in wet mode. 3. Permission scoping. The service account should not have blanket delete permissions. It should only be able to delete objects with a specific, temporary, tag. Our application code would be responsible for applying this tag, creating a clear boundary of what is safe to delete.
Now, it is your turn.
How would you design a safe and auditable approval process for the DRY run output? Describe a system that allows for automated approval for routine, low-risk runs but requires human intervention for high-risk or unusual runs.
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google Caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle is makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep: fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you had one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
the Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
17. The interview question.
You are on call. An automated deployment pushes a bad configuration to your authoritative DNS provider, accidentally deleting the primary A record for www.example.com. The error is caught by monitoring within 3 minutes, and the change is rolled back. Your authoritative servers are now correctly serving the right IP address. Yet, for the next 24 hours, the incident channel is flooded with reports of intermittent failures from users and partners globally. Your site is completely unreliable, but all your internal systems are perfectly healthy. What has happened, and what can you do?
Why Google asks this?
This question tests your understanding of the foundational, and often invisible, systems the internet is built upon. It is a scenario where the fix does not fix the problem, and the root cause is not a server, but a single integer, the time to live, TTL. It probes your ability to manage an incident where you are technically powerless to act, and your only tools are diagnostics and communication. It separates engineers who understand distributed state and caching from those who only think about the components they directly control.
What this tests.
1. Deep protocol knowledge. Do you instinctively know what DNS-TTL is and immediately connect it to the symptoms of a long, slow, intermittent failure? 2. Managing unfixable incidents. Can you formulate a response plan when there is no technical mitigation you can deploy? Do you pivot to communication and expectation management? 3. Distributed debugging. Do you know how to use external tools, DIG, global DNS propagation checkers, to diagnose the state of thousands of independent DNS resolvers across the internet? 4. Proactive design. Do you recognize that the TTL value is a critical design choice with a direct trade-off between performance and agility?
Common mistakes.
1. Chasing ghosts, wasting time debugging healthy servers, load balancers, or network paths because the DNS fix is already in. 2. Failing to communicate, not understanding that the primary job during this incident is to clearly and proactively communicate the nature of the problem, global DNS cache propagation, to users and stakeholders. 3. Trying to fix it, suggesting ineffective technical solutions like rebooting servers or trying to flush caches you do not control. 4. Not understanding TTL, being unable to explain why the problem is lasting for 24 hours, which is the core of the entire scenario.
Framework to tackle it.
1. Diagnose and name the problem. immediately identify the issue as a DNS cache propagation problem due to a high TTL on the now deleted record. 2. Verify global state. Use external DNS propagation checking tools to confirm that some recursive resolvers worldwide have the bad, empty, record cached, while others have the new, correct one. 3. Formulate a communication plan. Draft a clear, non-technical explanation for the public status page. Inform internal stakeholders about the expected duration of the impact. 4. Provide workarounds. Suggest that users with critical needs can try to flush their local DNS cache or switch to a different DNS resolver, like 8.8.8.8 or 1.1.1.1, that might have the correct record. 5. Postmortem and prevent. The root cause is a high TTL combined with a faulty deployment process. The fix is to lower the TTL and improve the safety of the DNS deployment pipeline. A model Google Caliber answer.
Step 1. Diagnose and name the enemy.
My first action is to name the problem correctly. Although we have fixed our authoritative server, the Internet is not a single computer. The intermittent failures are caused by the thousands of recursive DNS resolvers run by ISPs and corporations worldwide. Our A record had a TTL of 86,400 seconds, 24 hours. When we deleted it, those resolvers cached the does not exist, NX domain, response. They will continue to serve that incorrect, cached response to their users until that 24-hour timer expires. The incident is now a global DNS cache propagation issue.
Step 2. Pivot from mitigation to communication.
I must recognize that I have no direct technical control over these third-party caches. My primary role as incident commander now shifts from technical mitigation to communication and management. I will immediately update our public status page with a clear, simple message. We are experiencing a DNS issue causing intermittent connection failures for some users. A fix has been implemented, but it may take up to 24 hours to propagate fully across the global Internet. This manages user expectations and reduces support ticket volume.
Step 3. Provide workarounds and gather data.
While we cannot force a fix, we can offer guidance. We can suggest that affected users try flushing their local OS DNS cache or, for more technical users, temporarily switch their machine's resolver to a public one like Google's 8.8.8.8 or Cloudflare's 1.1.1.1, as these large resolvers often update faster. I will also use a global DNS propagation checker tool to monitor the situation, which gives me data to report on the progress of the recovery.
Step 4. Prevention, the TTL trade-off.
This entire incident was caused by a configuration choice made months or years ago. The postmortem will have two key action items. 1. Reduce the TTL. A 24-hour TTL for a critical A record is unacceptably rigid. We must lower it. I would propose a TTL of 300 seconds, 5 minutes. This is a trade-off. It will slightly increase the load on our authoritative DNS servers, but it gives us the agility to recover from a mistake like this in minutes, not days. The cost is worth the resilience. 2. Harden the DNS pipeline. Pushing a change that deletes a critical record should be impossible. Our CI/CD pipeline for DNS must have a linter or a policy check that specifically fails any change that attempts to remove the A record for www.example.com. It should be a protected record.
Now, it is your turn.
Lowering the TTL to 5 minutes seems like a good solution. What are the potential negative second-order effects of this change, particularly for a service with billions of global users? What specific metrics would you monitor after making this change to ensure it is not causing a new problem?
18. The interview question.
A new version of your primary microservice was deployed to 1,000 pods 2 days ago. Everything seemed fine. Then, this morning, you get an alert for a single pod restart due to an OOM kill. An hour later, 3 more pods are killed. Now, pods are being OOM killed every few minutes. The orchestrator is successfully restarting them, but the fleet is becoming unstable, and overall latency is rising as pods are constantly being terminated and starting up. What do you do?
Why Google asks this?
This scenario tests your ability to debug a slow-burn resource exhaustion problem. It is not a sudden crash, but a creeping failure that eventually triggers a cascading meltdown. The interviewer wants to see if you can move beyond simple metrics, like CPU, and diagnose issues at the process level. Do you have the vocabulary and toolset, profiling, heap dumps, to engage in a deep technical investigation with developers? It separates SREs who can only manage black boxes from those who can truly understand and debug the software they are responsible for.
What this tests.
1. Low-level diagnostics. Do you know what an OOM kill is, what causes it, and how to inspect kernel logs, DMESG, to confirm it? 2. Performance profiling. Do you instinctively reach for tools like PPROF, for Go, or other language-specific profilers to analyze the application's memory usage live? 3. Systematic isolation. Can you reason about why the failure took 48 hours to manifest? Do you connect this to a slow leak rather than a sudden allocation failure? 4. Safe remediation. Do you have a plan to safely test and deploy a fix without causing another outage? Do you understand canarying a fix?
Common mistakes.
1. The more memory fallacy, immediately suggesting that the solution is to increase the memory limit for the pods. This is a band-aid that hides the root cause and will likely just delay the next, bigger OOM kill. 2. Blind rollback, rolling back the binary without gathering any evidence first. While this might be a necessary mitigation, it throws away the opportunity to capture a profile from a running, leaking process, making the bug much harder to find. 3. Guesswork, looking at the code and guessing where the leak might be. A good SRE uses tools and data to prove where the problem is. 4. Ignoring history, not using historical memory usage graphs to clearly establish that the new binary has a different, steadily increasing memory footprint compared to the old one.
Framework to tackle it.
1. Correlate and mitigate. Correlate the start of the OOM kills with the recent deployment. Mitigate the fleet instability by immediately rolling back the deployment to the last known good version. 2. Preserve the evidence. Before the rollback completes, cordon off one or two of the leaking pods to prevent them from being terminated. Keep them alive for forensic analysis. 3. Diagnose the leak. Connect to the quarantined, leaking pod and use a memory profiler, like PPROF, to capture a heap profile. Analyze the profile to pinpoint the exact function or object that is allocating memory and not releasing it. 4. Fix and verify. Provide the heap profile to the development team to create a fix. Deploy the patched binary to a canary environment and monitor its memory usage for at least 48 hours to prove the leak is gone before rolling it out globally. 5. Prevent. Implement automated memory profiling in the CI/CD pipeline to catch memory regressions before they reach production. A model Google Caliber answer.
Step 1. Correlate and mitigate, while preserving evidence.
This is a classic slow leak scenario. The 48-hour delay between deploy and failure is the key. My first action is to initiate a rollback of the deployment to the last known good version to stabilize the fleet. However, while that is happening, I will immediately quarantine one of the pods that is showing high memory usage. I will use kube control cordon and taint the node it is on to ensure the orchestrator does not kill it and I do not lose my only sample of a running, leaking process. This evidence is invaluable.
Step 2. Diagnose with a profiler.
With the main fleet stabilizing, I will focus on the quarantined pod. I will connect to it and use our language's built-in profiler. For Go, this would be PPROF. I will pull a heap profile using Go tool PPROF http:// pod_IP:/debug_port/debug or PPROF or heap. This profile will show me exactly which function call stacks have allocated the memory that is still resident in the heap. I would expect to see a specific object, perhaps related to a new feature, showing gigabytes of allocated memory that should have been garbage collected.
Step 3, the fix and a safe rollout.
The heap profile is the smoking gun. I will provide it to the development team. The profile does not lie, it will point them directly to the source of the leak, for example, appending to a global map without ever clearing it. Once they have a patch, we will not deploy it directly to production. The fix must be deployed to a canary environment that mirrors production traffic. We will let it run for at least 48 hours, closely monitoring its memory profile. We need to prove that the memory usage graph is now flat, not slowly climbing. Only with that proof will we approve a full production rollout.
Step 4, prevention.
This outage was detectable before it reached production. I would propose integrating memory profiling into our pre-production integration testing pipeline. After a suite of tests runs against a new binary, we should automatically capture a heap profile. We can then programmatically compare the new profile against the profile from the previous release. Any new, large, or unexpected memory allocations would fail the build, preventing a memory leak from ever being deployed. We can turn this runtime bug into a compile time, or rather, test time, bug.
Now, it is your turn.
What's the difference between looking at the heap profile and the goroutine profile in PPROF? Describe a scenario where the memory usage is stable, but the application is still getting slower and slower over time. Which profile would you check first, and why?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle is makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you had one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
17. The interview question.
As part of a security initiative, you roll out a config change to your global load balancers to disable support for TLS 1.1. Your synthetic monitoring, which uses modern clients, remains 100% green. An hour later, the customer support channel for your enterprise customers explodes. A major client reports their embedded payment terminals can no longer connect to your API. Your primary dashboards show a slight dip in total traffic, but the error rate for TLS handshakes is still 0. However, digging deeper, you see a spike in a low-level metric, connections_closed_without_handshake. What is happening?
Why Google asks this?
This question tests your ability to see beyond your own state-of-the-art monitoring. It probes your understanding that your user base is not a monolith, it is a long tail of diverse and often outdated clients. It is a brownout, a partial failure, which is often harder to debug than a full blackout. The interviewer is evaluating your ability to balance competing priorities, security versus reliability, your empathy for different user segments, and your skill in using subtle, low-level metrics to diagnose a problem that your high-level dashboards are blind to.
What this tests.
1. User empathy. Do you immediately recognize that enterprise clients and embedded systems imply an older, less flexible technology stack? 2. Observability depth. Can you correctly interpret the difference between a failed TLS handshake, which creates a clear error, and a client that simply closes the TCP connection because it does not support any of the offered protocols? 3. Security versus reliability trade-off. Can you articulate a nuanced plan that balances the need to deprecate weak crypto with the business need to support paying customers? 4. Data-driven decision-making. Do you propose a solution based on gathering data about your clients, rather than making assumptions?
Common mistakes.
1. Dismissing the problem, saying TLS 1.1 is insecure, the clients need to upgrade. While true, this is not a solution to the immediate outage and shows a lack of business sense. 2. Ignoring the metric, focusing only on the 0 TLS handshake errors and failing to recognize the connections_closed_without_handshake as the smoking gun. 3. A permanent rollback, simply rolling back the change and calling the incident over. This solves the immediate problem but abandons the security goal without a plan. 4. Lack of a communication plan, not having a strategy to communicate with affected users before making a breaking change like this in the future.
Framework to tackle it.
1. Mitigate. Immediately roll back the configuration change on the load balancers to restore service for the affected clients. 2. Diagnose and validate. Correlate the incident timeline with the config push. Use the user agent string from load balancer logs to confirm that the failing clients are from older, non-browser systems. 3. Gather data for a new plan. Before attempting the change again, implement logging to actively track the percentage of connections that are still using TLS 1.1. 4. Communicate proactively. Use this data to launch a targeted communication campaign to the remaining users, announcing a future, firm deprecation date. 5. Execute a safe deprecation. Once the percentage of legacy clients is acceptably low, redeploy the change during a planned maintenance window. A model Google Caliber answer.
Step 1. Mitigate and confirm.
My first priority is to restore service for our enterprise customers. I will immediately roll back the load balancer configuration change to re-enable TLS 1.1. While that is propagating, I will confirm my hypothesis. The connections_closed_without_handshake metric is the key. It means the client and server failed to find a mutually supported protocol, so the client simply gave up and closed the TCP socket. This is a classic symptom of a legacy client. I will quickly query our load balancer logs from the incident window, filtering for these connections and inspecting their user agent strings. I expect to see agents like Java/1.7 or curl/7.19.7, confirming it is our target audience.
Step 2. Pivot from breaking change to data gathering.
The initial rollout failed because we were blind. We cannot try this again without data. The rollback is not the end of the project, it is the beginning of phase 2. I will work with our observability team to add a new metric, exported from the load balancers, that explicitly counts the number of connections per minute, broken down by TLS version. Our goal is to make the invisible, visible. We need a dashboard that shows exactly what percentage of our production traffic is still using TLS 1.1.
Step 3. Proactive communication and deprecation.
Let's say the new dashboard shows that 0.5% of our connections, almost all from our top 20 enterprise clients, are still on TLS 1.1. Now we can act intelligently. I will work with our technical account management team to proactively contact every single one of these clients. We will provide them with the data showing their services are using a deprecated protocol and give them a hard deadline, for example, 3 months from now, when we will permanently disable it. We will offer them technical support to help them upgrade their clients. This turns an outage into a customer engagement opportunity.
Step 4. The final, safe rollout.
Over the next 3 months, we will monitor the TLS 1.1 dashboard. As our clients upgrade, we should see the traffic percentage drop towards 0. A week before the deadline, we will send a final reminder. Then, during a planned, well-communicated maintenance window, we will reapply the configuration change to disable TLS 1.1 permanently. This time, because we did the work, the change will be a non-event. The postmortem will formalize this log, analyze, communicate, deprecate process as the official playbook for any future breaking changes to our public-facing protocols.
Now, it is your turn.
Sometimes, you cannot identify specific users, only their IP addresses. How would you design a system to temporarily exempt a specific set of source IPs from this security policy, allowing them more time to migrate while still hardening the protocol for the general public?
20. The interview question.
You are the SRE for a critical, multi-tenant feature flag service used by every other engineering team at the company. PagerDuty fires with a bizarre, high-level alert P0, global config staleness greater than 10 minutes. Simultaneously, the number one complaint in every support channel is, my feature flag changes aren't going live. Your core dashboards are a mix of confusing signals. The service's API availability is 99.99%, error rates are 0, and CPU is normal on 99% of the fleet. However, the central config coordinator pod is stuck in a restart loop. When it comes up, its CPU spikes to 100% for 30 seconds before it crashes. Because the coordinator cannot push updates, the entire global fleet of servers is now serving stale configuration. A simple rollback of the coordinator's binary does nothing. What do you do?
Why Google asks this, the cornerstone question.
This is the ultimate test because it simulates a failure in the brain of a complex distributed system. The problem is not a simple crash or a bug, it is a poison pill, a piece of user-generated data that triggers a pathological, emergent failure in the system's core logic. This scenario moves beyond infrastructure and into the intersection of application logic, distributed systems architecture, and multi-tenant fairness. It tests a candidate's ability to diagnose a problem that is invisible to traditional monitoring and requires reasoning about the system's behavior as a whole. Successfully navigating this proves you are not just a systems operator, but a true systems architect and diagnostician.
What this tests, the grand unification.
1. Systematic isolation. In a system with millions of pieces of data, the flags, can you devise a strategy to rapidly find the single, poisoned record that is causing the global failure? 2. Architectural reasoning. Can you look at the symptoms, coordinator crash loop, stale configs, and immediately deduce the likely architectural flaw, for example, a single point of failure in the config aggregation or distribution logic? 3. Deep observability. Do you know to look beyond metrics and into structured logs, application traces, and even core dumps to find the why behind the coordinator's CPU spike and crash? 4. Surgical mitigation. Do you have the discipline to perform a precise, targeted intervention, disabling one customer's data, rather than resorting to a clumsy, high-risk action, like trying to wipe the system? 5. Multi-tenant fairness. Can you articulate why a system that allows one tenant's valid but pathological input to cause a global outage is fundamentally broken from a design perspective?
Common mistakes, the traps for the unwary.
1. Focusing on the victim. spending all the time trying to make the coordinator pod stay up, for example, by giving it more CPU or memory. This does not solve the underlying data problem. 2. The blind rollback, repeatedly rolling back the binary, which the prompt says does not work. This shows the candidate is not listening and does not understand the problem is in the data, not the code. 3. Suggesting a data wipe, proposing to wipe the feature flag data store to let the coordinator start fresh. This would be a company-ending global outage. 4. Boiling the ocean, trying to debug by looking at the fire hose of logs from the entire serving fleet, instead of focusing on the single, crashing coordinator where the root cause is located.
Framework to tackle it, the SRE Masterclass.
1. Contain and analyze the coordinator, isolate the crashing pod from the orchestrator's restart loop. Capture its logs, traces, and if possible, a core dump or CPU profile during its brief, on, time. 2. Hypothesize the poison pill, form the hypothesis that the coordinator is failing while processing a specific, malformed, or computationally expensive piece of data, a single feature flag, from a single tenant. 3. Find the poison, use the captured diagnostics to find the needle in the haystack. The CPU profile will point to a function in a hot loop. The logs for that function should reveal the ID of the flag or tenant being processed just before the crash. 4. Perform surgical removal, use a breakglass admin tool or a direct, peer-reviewed database query to disable only the single identified poison flag. Do not touch anything else. 5. Verify and remediate, confirm that with the poison flag disabled, the coordinator starts up, stays healthy, and begins propagating fresh configs. The long-term fix is architectural, implement robust per-tenant resource limits and guardrails in the data plane. A model Google Caliber answer.
Step 1. Isolate the patient, capture the evidence.
This is a global correctness outage caused by a single component. My first move is to stop the bleeding in a way that preserves evidence. I will scale the coordinator deployment to 0 to stop the restart loop. Then, I will manually launch the pod on a quarantine node with enhanced debugging and profiling enabled. This allows me to analyze its 30-second life without interference. My primary hypothesis is that the coordinator is choking on a poison pill, a single tenant's configuration that triggers a pathological edge case, for example, a regex evaluation that causes catastrophic backtracking, or a rule set that's exponentially complex.
Step 2. Find the needle in the haystack.
With the isolated pod, I will capture a CPU profile during its 30-second spike. This is my most critical piece of evidence. The profile will show exactly which function is consuming all the CPU. Let's say it is evaluate_user_segment_rules. I will then examine the structured logs emitted by this function just before the crash. The last log line will contain the critical identifier tenant_ID equals 45821 and flag_ID equals A73B, CC91, EFF2. This is my poison pill. I now know the exact record out of millions that is causing a global outage.
Step 3. Surgical mitigation.
I will not touch the running system's code. I will perform the most precise, minimal action possible. I will use our emergency database access tool, with a peer and manager authorizing the command, to execute a single, targeted update feature_flag set enabled equals false where flag_ID equals, A73B, CC91, EFF2. This surgically disables the single poison flag. I will then restart the coordinator deployment. With the poison data neutralized, I expect it to start successfully, propagate the now slightly stale, but not poison, configuration, and then resume normal operations. The global staleness will resolve within minutes.
Step 4. The architectural postmortem, never again.
The root cause of this incident is an architectural failure to protect a multi-tenant system from itself. The postmortem will not focus on the tenant or the specific flag, but on the system's fragility. I would propose a multi-layered defense one. Per tenant resource quotas, implement strict validation at the API layer. No tenant should be able to create a flag with more than n rules or a complexity score above y. This prevents the poison from ever entering the system. 2. Graceful degradation. The coordinator's logic must be changed. If processing a single tenant's configuration takes more than X milliseconds, it should be skipped, an alert should be fired for that specific tenant, and the coordinator should continue processing the rest of the batch. The failure of one tenant must never be allowed to impact any other tenant. 3. Sandboxing. For computationally expensive operations like regex matching, they must be executed in a sandbox with a strict CPU time limit to prevent runaway processes from crashing the entire coordinator.
Now, it is your turn.
Describe how you would design the complexity score for a feature flag. What factors would you consider, for example, number of rules, type of operators, size of user lists, and how would you implement this check without adding significant latency to the critical API write path?
Check the comments section or description of this video. I have given a link to download a magical bundle that teaches you to develop Google caliber thinking and provides a complete mental model in a way that screams Google SRE. This bundle is the only end-to-end system that teaches you to think, act, and communicate like a Google SRE before you even set foot in the interview. It is the only structured playbook for Google's impossible rounds like NALS and troubleshooting. Most candidates sound like outsiders. The magic of this bundle is makes you sound like you already work at Google. Cracking the Google SRE interview is one of the toughest challenges in tech. Most resources only prepare you for parts of the process, a few coding problems here, some system design notes there. But Google's SRE loop is multidimensional. It tests how you think, act, and communicate. Imagine preparing with scattered LeetCode problems, random design blog posts, and still wondering how to survive the NALS round. That's how most candidates prep, fragmented, incomplete, and unstructured.
Now, imagine having one complete system.
Imagine instead you have one system that gave you everything.
A system that gives you
1. End-to-end coverage of every single round. 2. Playbooks that turn chaos like NALS and troubleshooting into structure. 3. Realistic practice drills that simulate the actual interview loop. 4. Insider language and frameworks that make you sound like you already belong. That's what this bundle does. It's not just prep material, it's a game changer because it transforms the way you think, act, and communicate into the exact style Google interviewers are looking for.
The Google SRE Interview Bundle covers
1. Recruiter screen and resume prep, tailor templates and scripts that pass the first filter. 2. Coding rounds, Python and Go question and answers designed for SRE-style reliability tasks. 3. System design and NALS, playbooks for both high-level design and Google's infamous NALS round. 4. Troubleshooting and debugging, a step-by-step handbook to master war room-style scenarios. 5. Behavioral and Googliness, real reliability scenarios that make you sound like you already work at Google. 6. Post-interview and hiring committee, an insider breakdown of how decisions are made. 7. Salary negotiation, recruiter-proof scripts and strategies to maximize your offer confidently. If LeetCode is practice mode, this bundle is the real game simulation. It doesn't just prepare you for questions. It prepares you to think, act, and communicate like a Google SRE before you even set foot in the interview.
For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development and more that will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers. For 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.